afternoon, everyone. My name is also Rahul, not to be confused by the organizer, Rahul Mital. I'm very happy to be here. It's coming out okay, the voice? All right. So I'll be talking about diesel aftertreatment, future challenges and opportunities. Aftertreatment basically refers to emission control or pollution control devices that are installed on diesel vehicles. I have to say that I definitely felt very out of place at this conference, attending the few sessions that I did. So much so that when I need a software upgrade on my laptop, I call my teenage son to help me out. So you can imagine my, actually I'm very honored to be here. Definitely very impressed and surprised by all the presentations. But I think I'm at the right place also, because what we are trying to do here with the help of Rahul here is to increase the awareness and interest in things like diesel aftertreatment and related technologies, because we think there is lots of opportunity. If you guys get interested in something like this, there is a lot of information available that can be data mined and help improve the system performance and customer satisfaction for GM vehicles. I hope I do better than this. So this guy is just taking away the chair from the session. I hope you take away more than a chair. The agenda of my talk will be that I'll quickly talk why we need this after treatment, a little bit about the basics, so it will help generate the discussion, what we have already learned and what we think are the opportunities, and then just one slide on conclusions. So GM has a lot of diesel vehicles around the world. In US, we are also trying to grow our diesel vehicle base. Currently, we only have the pickup truck, which you can see in the top figures. The Chevy Silverado is the most popular one. We also have GMC Sierra. We also have vans with diesel engines. But around the world, we have a lot of diesels. We have the Chevy Captiva, we have the Chevy Cruze, Beat, and for those of you who may not know, the Chevy Cruze is going to be offered in diesel starting this month. So, the importance of diesel after treatment is definitely growing. So we'll start with emission requirements. Why do we need diesel after treatment to begin with? So if you look at this chart on the top right corner, it's just showing NOx, which is nitrogen oxides, NO and NO2, versus particulate matter, which is generally the black soot that you would see coming out of diesel engines. Hopefully, you don't see as many now because things are getting better, but in the past, definitely there was black soot. So basically, the X and Y scale are those emission levels. In around 98, you can see this is where the blue box is. That's where the requirement was from EPA, Environmental Protection Agency, and CARB, the California Air Resource Board. In 2004, it went down significantly. In 2007, cut by another 50% on the NOx and 90% on PM. And then today, this is where we are, the red box. So you can imagine how the emissions are being tightened to keep the air quality better. This grid graph is essentially a comparison of Europe and North America. The idea is to show that every region of the world is basically heading in that direction. So in Europe, currently we are at Euro 5. Starting this year, we are going to produce vehicles in Euro 6 emission level. I'm not going to spend too much time on all the details and numbers. The idea of this chart is to show that this is where we are, this is where Europe is going. So as you can imagine, they need after treatment as well. This is where US is already today. So US emissions are definitely very, very stringent, and this is where we are going to go in the future. So all in all, the idea is that we need after treatment. So engine emissions can do so much. Engine, you can do the calibration and try to improve, but beyond that, it's the after treatment of the exhaust emissions that is needed to reach the emission levels required. Now there are a lot of emission systems around the globe, so there is a lot of opportunity to do many things. I'm going to focus on just one system because of the time constraint, but hopefully give you a flavor of what's needed. So this is how the underhood of the GMC Sierra or Chevy Silverado truck will look. So if you look at the chassis, that's how the after-treatment system will be installed. Just like a muffler and a tailpipe, you'll see all these converters underneath. Nobody gets to see them because we have no need to look underneath the vehicle, but these are all there. Then the body sits on top of the frame. So This is a diesel oxidation catalyst, a selective catalytic reduction catalyst, and then a diesel particulate filter. These are all again components. We don't have to really go in detail of each one. I will spend a little bit of time for the basics part, but again, trying to give you a flavor so we can continue to have further discussion later. So I'll start with the diesel particulate filter. That's the black suit that you see. You should not see any of that emission in any of the trucks starting 2007. So if there is a truck built by any OEM after 2007, it should be very, very clean exhaust. The reason is that there is a filter installed in the exhaust system which basically has alternate channels plugged. So the flow goes in like this, and as it goes through the channel, the channel is blocked at the end. It has to go through the wall and come out the adjacent channel. The adjacent channel is plugged in the front, so no flow can go from here. So as you can see, it's basically solid filtration. All the soot is collected into the filter, and over time, of course, it's getting loaded and loaded with the soot. So then we have to do some active management through engine combustion. We raise the exhaust temperature and burn all this carbon to CO2 and clean the filter, and then the cycle starts again. So it's a relatively simple concept, but there is an active control involved of maintaining its performance. That's where a lot of the calibration and diagnostics comes into play. We have a lot of sensors. We have multiple temperature sensors. We have pressure sensor, oxygen sensor to control all that, the kinetics and the regeneration or the cleaning up. That's called regeneration frequency. Another very, very important technology that's coming up in or very famous in diesel aftertreatment world today is the SCR, the selective catalytic reduction, not to be confused by the Siemens corporate research that will be coming up in the next few presentations. So this SCR technology, essentially there is urea injection in this technology done in the exhaust system, which breaks down into ammonia. The ammonia reacts with the nitrogen oxides, converts it into nitrogen. And in this case, also there is a ceramic substrate which has all the wash coat or the catalyst coated on it, but these are flow-through channels. There's no alternate plugging of channels. The flow just goes in this way, comes out that way. The idea of the catalyst is just to increase the surface area. What this chart is showing is again NOx emissions versus PM. The engine can do some sort of trade-off between NOx emissions and PM. If you increase the NOx, you can reduce the PM and vice versa. But if you need to be in this bottom corner, you have to use technologies like diesel particulate filter and SCR to make it happen. This bottom right graph again is just showing the emission levels for light duty vehicles. The one I showed previously was for heavy duty vehicles, but the bottom line is that we are in this top bottom corner and it's getting smaller and smaller. Now we'll talk about, now that kind of quickly covered some of the basics, the 20-year knowledge I have transferred in 2 slides, you can imagine. So now we'll go to catalyst parameters and diagnostics. So in terms of controls, there are almost as many variables and control parameters on the engine control module for diesel aftertreatment as they are for the engine. So you can imagine how big this whole system has become and how critical it is also, because you can make a vehicle just like you cannot sell it without an engine, you cannot sell it without the aftertreatment today. So it is very, very critical. So of course, in addition to all the sensors we talked about, there are all the engine hardware that also impacts the performance of the system. So like the turbo machinery or the fuel injection system, for example, if the engine combustion does not happen properly, it will change the engine out emissions of the NOx and PM, and that significantly impacts how the after-treatment system will respond. And all that has to, it's like we are at the tail end of the whole process. So any failure mode upstream impacts us downstream. So it becomes very important. So this list that I'm showing are just some of the parameters that need to be monitored or we should be cognizant of to control performance of our system. A list of some of the, when you see that red light on your dashboard, the check engine light or malfunction indicator light, behind that is all sorts of codes that the dealer that plugs in and figures out why you have a check engine light. Because when you go to a dealer for service, they actually need to know what hardware went bad or what the issue is. And I just circled a few. I know it's a very small font. I didn't expect anybody to read. But the point is these are all like catalyst efficiency codes for either the VOC or SCR or DPF. And that's how the dealer figures out that, okay, this is the area I have to concentrate to fix the vehicle. Now we'll talk about the most important part. How much time do I have? 4 minutes? Okay, we should be okay. So this is why there is, of course we have learned some lessons, but why we think there is opportunity. What this pie chart is showing is just the 3/4 of our parts that come back from the field that we analyze are called NTF. NTF means no trouble found. And that's very, I mean, it's good in some sense. We say, okay, the hardware was robust, but it's bad in the other sense because we replaced so much hardware and it was inconvenience for the customer to come to the dealer, and it's a cost to GM because all these parts are generally under warranty, that we are spending all this money. Why this is happening is because when a quote comes in, the dealer makes a judgment call to say, okay, I should maybe replace this hardware. And what I think is happening is our service procedures are not as clear or as detailed because these are all new technologies and a lot of things impact the performance of these technologies. So what we are trying to do is do better data mining and get more information sooner so that we can help this whole process. And that's what I really wanted to focus on in the next 3 minutes now, I guess. These are some of the lessons learned. For example, normally a catalyst performs the best when it's fresh, and as it ages, its performance deteriorates for various reasons. It could be temperature causing sintering or poisoning of the catalyst. But there are certain technologies which actually need some sort of activation. And if your calibration is defined for best performance at the beginning, and then of course we take into account the aging effect, but there is a green catalyst effect that sometimes the catalyst needs some sort of temperature treatment before it will come to its peak efficiency. And if that is not taken into account, you will get lots of false codes. Well, they are not false codes, they are real codes, but the catalyst was actually going to improve in performance. But by the time the dealer replaced the hardware and we got the hardware back, it was actually performing well. But there was a period where it was not performing as efficiently. So those were the kind of lessons learned that we realized we need to take into account. And again, there was how long do we need to monitor to diagnose something? So those are, we realized that we need to do it on multiple drive cycles because every customer drives differently. So those we call exponentially weighted moving averages. And then every customer drives differently. There are actually people with these heavy duty trucks that leave them idle for many, many hours. And that changes the performance of the system. But in each case, the point is that we learned about these over time, but we also felt it took us very long to figure those issues out. It would have been much better if we could have found those issues sooner. And this is really the crux of the whole issue here in terms of the real-time data analysis or the cloud that's available that we can use. In our case, we don't need like every second or every minute or every hour. Even a couple of days or even a week or 2 weeks would be okay. Because right now what's happening is we have the vehicle is built at the plant, it's delivered to the dealer, dealer sells it to the customer, customer observes an issue over a certain period of time. At some point, depending on the severity of the issue, the customer goes to the dealer, and then the dealer fixes the problem, puts the claim in the GM system, and then we do the data pull to understand what's going on. And we do data pull for parts that have very high warranty, of course. So this process can take 3 to 4 to even 6 months. And for those 6 months, not only we are having issues with the customers, we are building vehicles every month with the same issue for the next 6 months, right? So those vehicles will come on the road. So again, the whole point is that the sooner we can get this information, the better. And the things that we think we can actually take advantage of with our new technology or the information system is any manufacturing defects we have. Like I said, if we can isolate the fault specifically where it is, as opposed to saying it's in the general vicinity of the after treatment, or there is sometimes one fault code triggers multiple fault codes downstream, but the dealer actually does not realize that this was a root fault code, and they fix all the fault codes, which again is unnecessary expense. We could probably take some action remotely to fix those issues. At least we could provide specific service procedures so the dealer can do the work efficiently and faster. And then there is no limit. I think I'm talking about diesel after treatment, but GM of course makes millions of gasoline vehicles, so we could apply it there. And then why limit it to after treatment? You can apply it on the engine and the whole vehicle. So my last slide basically is hopefully I presented an opportunity to work on in the area of automotive industry. The demand for efficiency is very high from these systems. So what that means is that we are working in a very narrow range of diagnostics. So any shift into the system or system performance can easily trigger a code. And if we can diagnose it properly, maybe some of those are actually just false codes and we can prevent any hardware replacements. We have learned quite a few things, but with the advent of cloud computing, and we have OnStar on GM vehicles, some of you may know there's a blue button that you press. So there is a lot of opportunity to collect data and process and come up with strategies to quickly fix issues. And our stretch target could also be to actually take some actions remotely and fix the problem if it's fixable through software without actually having the customer to come to the dealer. It will save everybody a lot of time and money. Thank you so much.
We have time for 2 questions.
I was crystal clear, I think.
Thanks for that. One of the questions, sort of, let me think this is for most of us who are not familiar with these systems, is how do we get models of these systems or sort of access to some information?
Actually, I forgot to go to my last slide. So, actually, the reason I'm here is because there is some initial discussion already happening with Rahul's team here. I think that is somewhat of an issue. I think Rahul's team has been asking for some field data. I would like to provide, and I am going to provide some of that data. I think a collaborative effort would be required because these are sensitive informations. Giving out those models that we develop are definitely proprietary and sensitive. But there are examples where people do this. Maybe the short answer is that we will have to get together, come up with an agreement of confidentiality to say, okay, we're helping each other. And I think it can be done. People are doing it. Just that, yeah, it's not as easy that I can just ship it over.
So if I could also insert over here, this is an example of a very interesting cyber-physical system where we want to sort of say have cloud computing, the car and the cloud interface with each other, but there's a lot of messiness that even if you have a design time model, it's very hard to see how the system is evolving. So Rahul will be around at the coffee break afterwards, and the idea is that we are coming from very different sort of domains, and where even the language and the jargon is quite different from the deep mechanical end to our CPS computing and control systems end.